Welcome, esteemed colleagues and fellow scholars. Today, we delve into the enigmatic realm of primordial black holes, entities that predate the earliest stellar formations. This discussion aims to unravel the complex nature of primordial black holes, what they are, their genesis, and their profound implications on our understanding of the cosmos. Primordial black holes, hypothesized to have formed during the earliest epochs of the universe, represent a paradigm distinct from stellar black holes. Consider the fluctuations in the primordial plasma during the inflationary phase. Curvature perturbations exceeding critical thresholds could collapse, overcoming the radiation pressure to form these black holes. Various formation mechanisms have been proposed, from the energetic landscapes sculpted by cosmic inflation to the dynamics of bubble collisions during first-order phase transitions. These black holes contain masses that reflect the universe's Hubble parameter at their time of genesis, serving as profound probes of early cosmological conditions. Due to Hawking radiation, primordial black holes evaporate, a process dependent on the black hole's initial mass. For those with masses less or equal to 10 to the power of 15 grams, this process culminates well before the present epoch. The evaporation releases a spectrum of particles, primarily influenced by the black hole's decreasing mass. Current observational data delineate constraints on their initial abundance, offering clues on whether these entities contribute to dark matter or induce nucleosynthesis anomalies. The Big Bang Nucleosynthesis, BBN, is a cornerstone for understanding cosmological conditions. PBHs engage this era by injecting energy through Hawking radiation, altering the established synthesis of light elements. The photodissociation of nuclei, particularly helium, mediated by lower energy photons released by evaporating PBHs, introduces variations in expected primordial abundances. Herein lies a critical constraint: the balance between energy scales influencing elemental syntheses and PBH-induced disruptions. During the terminal phases of black hole evaporation, localized hotspots form in the radiation fluid surrounding the PBHs. These regions have higher temperatures, altering the efficacy of photodissociation processes. The hotspot creates a thermal gradient that functions as a temporary barrier against the free propagation of low-energy photons. The precise temperature profile is a critical aspect, influencing whether PBHs silently adjust light element abundances or emerge as detectable anomalies within nucleosynthesis records. Hotspots substantially affect the photon emission rates. The reprocessing of particles within a hotspot can mask or modify the expected emission spectra. Experimental models must consider the differential cross-sections for photon interactions, particularly in dense, high-temperature plasma environments. A detailed analysis reveals that while primary Hawking emissions are affected, the diffusive flux within hotspots can often exceed initial predictions based on homogeneously distributed emissions. The resultant low-energy photon spectrum ultimately shapes observables post-cascade interactions. Here, the universal spectrum offers a quantifiable measure of reprocessed photons at varying energies. Observations hinge on accurately calculating transfer functions, which shift depending on initial PBH mass and evolutionary dynamics. The presence of hotspots necessitates a re-evaluation of these constraints, demonstrating that energy deposition and thermal gradients influence nuclear disruption potentials beyond prior estimates. Recent studies provide compelling evidence indicating that hotspots significantly influence observational constraints obtained from primordial nucleosynthesis datasets. Particularly, for masses ranging from 10 to the power of 11 to 10 to the power of 12 grams, shielding effects reduce the photonic impact on nuclear disassembly. Moreover, estimates suggest that conclusions regarding PBH's influence on BBN physics may need revision to accommodate these localized temperature variations. In conclusion, primordial black holes offer a unique window into the universe's nascent conditions. By comprehending their formation, evaporation, and the associated hotspot dynamics, we refine our insight into both cosmological history and particle theory. As future inquiries unfold, we anticipate groundbreaking revelations regarding these ancient cosmic entities. Thank you for accompanying us on this intellectual voyage through the early universe. Should you wish to explore further, subscribe and join us next time as we continue to uncover the secrets of our cosmos. Leave your thoughts and questions below. Your insights propel our cosmic conversation forward.